Okay, good afternoon, ladies and gentlemen, and thank you, Louis-Philippe and co-organizers for the event. I'm learning a lot myself, and it's a pleasure to share with you our results, experimental mostly, on patterns silicon membranes. So the work is being done at the Catalan Institute of Nanoscience and Nanotechnology in Barcelona. And people involved are named here: Bart Grzynkowski, now in Germany; Francesca Alsina; Markus Wagner, now in Berlin; Mariana Sletzinka; Emilio Chavez Angel, also now in Germany, soon back in Spain; Alexandre El Sachat, a PhD student; Sebastian Reparaz, who was in Germany and now probably back in Spain. And you know, I don't actually do the experiments anymore. It's very sad to admit. The group is about 20 people, and our main research lines are in nanoscale thermal and acoustic effects in thin films and nanostructures. We are also working on optomechanical systems at room temperature. You will see why in a minute. And to make our structures, we need to work on nanofabrication, lithography, and in particular, we've been working on metrology, how to assess the deviations from the desired pattern and structure. So combined with nanofabrication. The work I will be talking about has a background that has been made on investigating in collaboration with a number of colleagues. So some of the names you know are here, particularly David Donario and Luis Felipe Pereira, John Jacopelto VGT, our colleagues who introduced us to PAM-PAM probe spectroscopy or picosecond acoustics, and colleagues who help us to understand the ins and outs of light scattering. So how do we actually model and simulate the shapes of Raman and Brillouin signals? And general discussions and some joint experiments with the MIT groups of Keith Nelson and Gang Shen. And of course, you always need some funding for experiments, so over the years, these are the projects that have helped us pay people and consumables, etc. I want to give you two examples of the work we do in the group, and you'll see the connection to phonons and films and silicon. The first one refers to the interaction of mechanical modes with light. So this is in the range of optomechanics, coupling the motion due to light pressure to here to a mechanical mode, here depicted as a spring. In reality, these systems use a nanobeam. It's a silicon suspended nanobeam, which is designed in such a way that it has a phononic and a photonic band structure. So here you see the light cone, and this is my phononic part with a phononic gap. And here you see the dispersion relation as the band for the mechanical modes also with a gap. And so this picks up certain resonances when they couple, and others are induced by bringing light through an optical fiber, coupling the light modes to the photonic modes, which in turn couple here to the phononic or mechanical modes in the system. And the light that is transmitted is our signal that enables us to study the phonon-photon interaction. Most of experiments until we started work in this area were performed at very low temperatures, 4 Kelvin and so on. And we decided that to put up with real life, which I think is quite a challenge, but why not? Stands better chance of being used. And we work at room temperature, and we decided to stick to silicon for obvious reasons. When you have to make these structures, reproducibility plays a tremendous role, and you have to have a means to repeat the structure and make it again. So the optical signal affected by this interaction gives you peaks in the structure that are associated with the particular modes, the mechanical modes of a system. So they appear frequencies of 4 or 5 gigahertz. So this is a very exciting regime for a number of telecom applications. And we work, as I said before, at room temperature and in air. Many of these interactions are affected by what is called the thermo-optic and free carrier dispersion effects. It is a combination of these two effects that shifts the resonances of our interacting phonons, phonon cavities, and then these particular terms here that depend on temperature, and the other one depends on carrier concentration, will provide two competing mechanisms. And these mechanisms will result in the system pulsing the particular frequency that is being selected. Pulsing means that you have like an oscillator. And in the case here, when the frequencies are locked, you have a particular shape of the pulse that you are detecting. You have a significant change when they are unlocked. And what is very interesting is that you see, like in lasers, a line narrowing for the coherent mechanical oscillations. Not to go into a long story, there are several regimes, but perhaps the most important one is that this self-pulsing, this interaction of a temperature-related effect and a free carrier absorption-related effect gives you a train of pulses that in the language of optics is called a frequency comb. So this is used in metrology for clocking, but it's also, in reality, is like a phonon source. So we use these, our current project is to use these type of signals as a phonon laser, effectively. The second example, and we actually had a little shot to see if we could relate the Q factor to the thermal conductivity. And basically, depending on the resonator frequency, one sees that there is a dependence of 1 over the frequency and the lifetime of the thermal phonons, which actually has a minimum. Or you could perhaps shift this one here and see that there is a clear dependence of a Q factor of a resonator, the thermal conductivity of which will be diabolic to model because it is a beam with holes, varying periodicities, etc. So we are testing these calculations now and see if we can, by measuring Q, we can extract perhaps empirically the thermal conductivity without really understanding too much as to the mechanism of it, but at least as a measure, because this is precisely, Q is an indication of how good your resonator is and the kind of losses you have. And we know we have losses due to the thermo-optic effect and carrier density. So the second example has to do with what our chairman talked on Monday, which is thermal conductivity in molybdenum disulfide. So we obtain polycrystalline molybdenum disulfide, exfoliated and put it on an electron microscope grid, and proceeded with our experiment. So here we use the technique that Joni Ahopelto explained to you on Monday, basically laser Raman thermometry. First of all, we studied the Raman spectrum of polycrystalline molybdenum disulfide. We saw that this is a very good peak to focus because in the nanosheet it also appears strong, okay, shifted, and we use this one to measure the temperature of the molybdenum disulfide membrane as a function of position. And it gives us this, this temperature field as a function of a point across the membrane, basically going from temperatures up to about 600 Kelvin, so showing 300 degrees of heating, and looking at the detail of the experimental data on the left side and on the right side. There's a slight difference, which we explain in a funny way, but the bottom line is that the thermal conductivity is around 0.7, 0.75. That is 1/100th of the thermal conductivity in the bulk of molybdenum disulfide. So it's a factor of 2 orders of magnitude reduction. The data was explained on Monday. We have to take care that we use the absolute powers here, and these experiments are done with 5 different detectors to get the reflected, transmitted, etc. light. The membranes being a few nanometers basically means that 99% of the light goes through. So the actual power absorbed is minimum itself to avoid things like creation of photoexcited carriers and so on. Polycrystalline means that it has grains. Grains means that you have a distribution. And so we ran, first of all, SEM analysis of the grains. We saw a distribution of those. We saw that we had a majority of grains in the few nanometers, so 3 to 5. And the model that was made took into account percolation of phonons in these grains. The important bit is that there is a gradient of grains, and this actually led to the difference between the left and right values of the thermal conductivity. But the model allowed us to see the thermal conductivity dependence, or maybe I should talk about thermal conductance, on grain size. Right? So the experiments we had were in 0.7 watt per millikelvin. These are the values. I don't remember where these values came from, maybe from a previous slide. But these are the values that are depending on the grain size. So we think that it's a percolation-like propagation of phonons. They basically go and scatter off grain boundaries. The conductance is of 87 megawatt per meter square Kelvin, and the conductivity then scales up to a certain size. After that, it begins to deviate quite dramatically. And this is perhaps not necessarily surprising, because in the size regime of 10 nanometers or so, you start to have grain boundaries which are significantly larger than the wavelengths of the phonons, acoustic phonons in particular. So we continue with this work. We have a very long list of questions. But this is not about molybdenum disulfide today. So the purpose of this talk is to share with you our findings concerning what happens in this system which, compared to what has been discussed so far, has a very large number of atoms, very large lateral sizes, but nevertheless, they displayed a wave phenomena, and because they have certain order, and even when they don't have certain order, they still behave, as far as phonons is concerned, as if they were waves. So I'll tell you why we're doing this. Introduce the 2 cases of phononic crystals we were working with. I'll tell you about the dynamics of these structures, and in particular the effect of disorder on the thermal conductivity. Then we will talk about the geometrical effects on this, like the necks that form, the surface to volume ratio, and or porosity at the end of the day. Okay? So in terms of phononic crystals, there are at least 2 strategies to control the thermal conductivity. One is based on controlling the placing and a number of scattering centers, be these impurities or be these defects. And the other one refers to changing or engineering the phononic band structure so that you can have gaps or regions where phonons cannot propagate, or regions where phonons travel slowly. So flat dispersion relations. And in particular, we decided to work with holy, or this type of membranes with holes, holy phononic crystals suspended, and basically the community is working on silicon, silicon nitride, gallium arsenide, etc. You will see that one of the key parameters, geometrically speaking, is this neck And the neck here is defined as this material between two holes in the pattern. Right? So we will see that our neck effects are set around 15 nanometers, depending on temperature. There are different approaches to study that. And one of the heated debates has been whether we do have coherence effects in phononic crystals. So the neck effects came about when this type of two-dimensional phononic crystals were studied. So these are fairly disordered, or you can describe them as meshes, as a mesh. And the thermal conductivity was measured here as a function of temperature for membrane-like and then different separations of holes. And compared to this little line with open squares, which is the amorphous silicon oxide regime. Okay? So basically here the thermal conductivities were in around the lowest ones of a few watts per meter Kelvin at room temperature. So this regime here. Also, the temperature dependence of the thermal conductivity at low temperature was studied, and there were some laws that were identified, which we will discuss a bit later. Approaches to understand this was to see, well, particularly the group of McGaughey in Carnegie Mellon, they have tried to understand how the thermal conductivity depends on the degree of porosity, because you're making holes in the membrane. And they can explain very well by this method called free path sampling the in-plane thermal conductivity. So theory experiments, experiments from Sandia National Lab. But it gets a bit complicated when they come to the cross-plane. This is not a surprise, actually, because the measurements cross-plane of this type of material is quite a challenge. Right? You need to put thermometers and be sure that you actually measure comparable volumes, etc. So maybe the theories at the end of the day is right, but it's still to be confirmed for the cross-plane thermal conductivity. Exactly. So you go in different directions. You define your degree of certainty by the number of nearest neighbors, and so on. It's not much more than that. It's not a method we use, but it seems to be adequate. So about 2 months ago, the status of understanding, or measurements at least, of thermal conductivity in phononic crystals at room temperature could be summarized as follows. First of all, a range of geometries had been tried. Right? So we had square patterns, hexagonal, honeycombs, etc., various surface to volumes ratio, silicon, polycrystalline silicon, silicon nitride. The experiments were done mostly with time differential thermal conductivity, and there was an agreement, more or less, that the coherent effects were only present at very low temperatures. Well, very low in this community, maybe millikelvin, but few kelvins and below. There's also an agreement that the inhomogeneous parameters include surface roughness, which is quite serious when talking about making nanostructures. It includes doping, whether it is intentional or unintentional, unintentional being residual doping, isotopes, etc., and defect concentrations, which is not only how many you have per unit volume or area, but also how homogeneously they are distributed, right? So these were the kind of experiments done, and I showed you where the status was. There is pretty much an issue concerning most of these points. The rest of the talk is organized in such a way that I thought I should give you the conclusions first, or at least a take-home message, as it sometimes is called. And our experiments show that the surface-to-volume ratio itself hardly impacts the thermal conductivity. But the geometrical factors which are very weak at room temperatures, can be about a fifth at low temperatures. We also find that the concept of mean-free passes still applies, but you need to consider the necking effects. And depending on a combination of a surface-to-volume ratio and geometry, you can have a scope to tune the thermal conductivity of a 2D phononic crystal, which is already significantly lower than the bulk. So, we'll start with two case studies. First of all, this is a membrane, so no phononic crystal here. So, our membrane is made in a way slightly different from what Johnny Ahopelto mentioned. We actually open some holes to allow the etching of the underlying silicon dioxide and have it suspended. It is about 250 nanometers thick. Is silicon on insulated starting wafer. We characterize the membranes by inelastic light scattering, brilliant scattering, and that gives us a peak into the resonances in the material up to about 30, 40 gigahertz. And with very clear peaks that can be plotted on a dispersion relation curve. This is a calculation. We use COMSOL for these type of things. And if one varies the angle of incidence on a sample, you have the projection on the plane, and that allows you to measure the different wave vectors. And so these are the various points. This means that they have been measured at different angles, and they map the dispersion relation. So we have a very good understanding of which peak belongs to what symmetry and to what band. So we have symmetric, asymmetric modes, shear, dilatational, you name them, right? And this is why, and this is a relationship we use to obtain points different from zero, from Q equals 0. Okay, so this is our starting material. Then we decided to fabricate two types of phononic crystals. One, where we would be modifying the periodicity by introducing holes. So we would then have Lamb waves that would travel on the membrane, traveling in a holey structure. This periodicity would open gaps due to Bragg reflections. So our dispersion relation would look something like this. And this is with respect to the plane, the parallel. But if on the other hand, instead of making a hole, we add a set of resonators periodically positioned, then we would have the interaction of Lamb waves with the resonator frequencies. In fact, there is then a coupling of these, and with the periodicity, we have effectively this dispersion relation plus the resonator mode leading to hybridization. And that means that we have, of course, Bragg reflection, hybridization, and then we would have both propagating and non-propagating modes. Sorry, my cold. So these are the CM images of the structures. So this is our starting material. These are the holey structures, or what we call air-solid phononic crystals. And these are the ones, these are the metal parts. These are the pillars or resonators of gold on the membrane. Yeah. So here is a depiction of experimental geometry. So incident laser light reflected, transmitted, scattered, and coupled to the material. So we now take a look at the holey ones, or the solid air. Brilliant scattering showed us a rich set of peaks, which can be all placed in the dispersion relation. Shows very clear, it's amazing, the agreement here. We have a description of the symmetry of these peaks, that is to say, we know how the amplitudes of the displacements look like around around holes for a particular mode. Yes. So having this type of solid air, or the holy ones, we see that there is a modified relation dispersion. There is some folding. The frequencies crash or go down dramatically. There are frequencies that are forbidden, so we actually open regimes where there is no phonon propagation. We preserve the mid-plane geometry, and we have a mixing of polarizations, which is like happening here, most clearly perhaps in this regime. The solid-solid phononic crystal, by contrast, have, again, this is our workhorse, brilliant light scattering. We pick up all the relevant scattering peaks along the gamma x direction. And you can see there is a serious difference in the dispersion relation here. So we basically have put resonators that absorbed energy and slow down the propagation of waves. So the hybridization has these two impacts on it. So instead of having a broken mid-plane geometry that is gone, because now we have added something on one part, there is hybridization and localized modes. There are propagating modes. There are a series of flat branches, phononic branches, which basically says very slow phonons. And there is indication of three-dimensional localization, because, for example, here in this lower mode, the X1 and the X2, the amplitudes are largest inside the pillars, inside the resonators. Right? So this is the macro picture compared to the resonators that you were talking about on the surface resonances. In your case, 1 or 2 nanometers. In our case, 100 nanometers. Okay. These are 60 nanometers or so tall. Dramatically. Yes, of course. But this is exactly the point. The physics are the same as long as we describe this with waves and with resonances. This is the important bit. So in the wholly phononic crystal case, we would be in a regime of up to 20 or 30 gigahertz. In the case of the resonators on a membrane, we are in the regime of below 12 gigahertz as well. Okay? So to summarize, these phononic crystals exhibit modification of Lamb waves, some folding, negative group velocities, downshift of frequencies. There is a range of forbidden frequencies, or a phononic gap. In the case of the holy crystals, or air solids, we also have mixing of polarizations, but they keep the mid-plane symmetry of the mode. In the case of a solids, we have a hybridization of localized modes and propagating modes, plus the 3D localization. Okay, so that's the story on the characterization of phononic crystals. Yeah. Yeah. This is 250, and this is, I don't remember, I think this is like 60 or 70 nanometer tall. Oh, yes. Yes. And they're not actually perfect cylinders. Huh? I mean, so these things, there are some geometrical things important here. Yeah. Okay. So I'm going to tell you something then about the lifetimes, or the time scales, what happens with the modes in the time domain, and how that impacts or not the thermal conductivity. So when we talk about disorder, there are several types of disorder, and you need to think which ones are more suitable to be viewed from a waves perspective or from a particle perspective. I will take no side on this. First of all, there is a disorder that has to do with position. It doesn't mean that you are different material, different size of hole. It basically says that the holes or the resonators are off their expected periodic positions, right? So that Mickey Mouse picture here. There's another one that has to do with the size or dimensions. So some of the holes or pillars, for that matter, could be much larger, others smaller, some elliptical, etc. So it's another type of disorder and has a different metric. There's another disorder type which has to do with symmetric or asymmetric structures. So you could make cones that are upside down. You could make holes that are perfectly rectangular, some which have this conical shape or inverted of that. All that is going to contribute to the band structure of the phononic crystal. And then you have the much vilified surface roughness. Right? So the surface roughness picture that we take from Siemens looks something like this. There are some atomic steps, some little holes, and you describe these by a particular size, and one thinks of it as a random roughness, and one that can produce a specular reflection or be highly dissipative and change not only your phase but also your amplitude. So those. There is finally another type of disorder which is chemical. For example, some atoms are going to be replaced by, say, impurities, typically carbon or residues of polymers, mask, or something else. If you do it properly, isotope doping or ion implantation or whatever, you can do this in purpose as well. In what follows, we got stuck here. We are only going to look at positional disorder, which is, and it will not change more than 10–15%, so it's a small one. So the frequency regime that we will look at is in the hypersonic regime. Experiments are by asynchronous optical pumping spectrometry. Spectroscopy is a type of pump and probe. We calculate the dispersion relations by FEM, and we measure the thermal conductivity by 2 laser Raman thermometry. Typical samples, 250 nanometer, lattice period about 300 from center to center. Right? And here you have the order and the disorder, the positional disorder one. So this is just for illustration, the frequency range going to 10 terahertz, and in wavelengths going from 100 to 1 nanometer here. So that's where we are pretty much. And experiments are done on, well, we measure the surface roughness, we obtain an estimate of the wall of the hole's roughness of about 7 nanometers in worst case, and the lattice displacements in the disordered structures can be up to about 22 nanometers. So like 10%, 7% of the period. Schematics of experiment. Here is the pump and probe experiment. So pump of 1 wavelength, probe lower energy, different one, repetition rate 1 gigahertz, and line width of 10 kilohertz. For the thermometry or the thermal conductivity measurements, we use 2 lasers. We use a heating laser here, is blue UV, with an objective, and it doesn't say anywhere, but this one has 2 to 10 times more power than the scanning laser. So I think typically it's 8 to 4 or 8 to 1 milliwatts. And this is the laser that will be scanning the temperature. So the pump laser and probe laser are placed in some area of the phononic crystal. And the large picture is that you have a very fast electronic response. As soon as there are flux of photons impinging on the sample, you have a generation of electronic excitations by a photon-electron interaction, which is very fast. Is something in this time scale is just a peak. And then you have a set of oscillations as a function of time, which, when amplified, give you information that you can extract taking the Fourier transform of that peak. And that is what we call the lifetime of our phonons. These oscillations vary with respect to the reference membrane, the order membrane, and the disordered one. All these in the scale of 1 nanosecond. And if we take this further, taking the Fourier transform of that, you see a family of peaks that become A, fewer, and B, all shifted to lower frequencies. Right? So that's the influence of disorder on the lifetime. But curiously, or on the mode distribution of this, of the lifetime of the phonons. And here you have a little bit more explicitly the frequencies that are involved, right? These are frequencies that are seen in also in, these are ascribed to the frequencies observed in brilliant light scattering. The membrane dispersion relation, as we know it, is here, and in the time domain we can identify very well the gamma equals 0 frequencies. The order phononic crystal also has a very well described dispersion relation, but you see that all the frequencies have come down. And the out-of-plane modes have intensities that vary. So this is higher amplitude, and then they lose the amplitude, some recover it, etc. But all these peaks at 0 wave numbers, they are explained and ascribed as per the previous measurements. So yes, as in the previous case, we have evidence, more evidence on the modified dispersion relations. There are modes which have a non-zero out-of-plane displacement. These are particularly here. And there is a 3D displacements of all the modes identified as shown here. So these are the modes depicted from FEM, the unpatterned membrane, and then the modes of the order phononic crystals, which go from 16 gigahertz all the way to 50-something gigahertz. Yeah? And so these are fairly well described and documented here, amplitude and polarization. To measure the thermal conductivity of these samples, we use a laser Raman thermometer, as I mentioned, and what we obtain are temperature maps of ranging from the center, or rather where the laser is, away and radially out of this point. The temperature is obtained from the shift of an optical phonon that we track that has been suitably calibrated. We use this expression to obtain the thermal conductivity, the temperature fields, and from the slope, we obtain the thermal conductivity. Key parameter here is a power absorbed. It was quite involved calculation considering all the scattering from this type of holy structures, with disorder and without disorder, etc. Nevertheless, it was possible for us to establish, without any doubt, that disorder that positional disorder hardly plays a role in the thermal conductivity at room temperature in these structures. Okay? So let us now go and see the thermal conductivity into the phononic crystal, but paying a little bit more attention to the next, the surface to volume ratio, or what I think we are down to call the porosity. Okay, for this structure, we decided to change a little bit the sample design. And we decided to put a metal, to deposit a metal as a heater for our crystal. So this is where we put our laser. This is the metallic, this part here. And we measure scanning away from the heating spot. So typically, this is what we would get. This change of slope is because here we're in the metal part, and here we're in the phononic crystal part. So The diameter of these phononic crystals are 100 micrometers. The island is 5 microns. The periods are in the few hundreds of nanometers, as in the other case. The whole diameter is in the hundreds. Instead of using other geometries, here we use a square lattice, and the thickness of the whole membrane was a quarter of a micrometer. By this time, we also had been very aware that we had to measure both in vacuum and in air to be consistent with the measurements that were done before when we were comparing our measurements to the Vires calculation. And so here we have data for one crystal with a periodicity of 200 and holes of 130 nanometers. So the profiles in vacuum, they reach higher temperature because there is no convection to take heat away, no air convection. And here it is the comparison, red in vacuum, blue in air. So that's a temperature versus position. The slopes for vacuum and air are shown here, and the steeper slope in vacuum corresponds to a lower thermal conductivity, as shown here. So we were able to measure the thermal conductivity up to about 900 Kelvin. What we observed, I think the message is that we observed a 50-fold reduction in the thermal conductivity at 350 Kelvin. And similar trend was observed for the other period. The temperature fields now, with respect to the filling fraction and the volume, are here. So you can compare here the 250 membrane, temperature in air and in vacuum. Here the position of a temperature with respect to the logarithm, the temperature field for another sample, and we put here the volume reduction factor for the 3 geometrical arrangements, which corresponds to this filling fraction. Yeah. So there is a dependence on how much material you have left, the volume reduction, the surface to volume ratio, but it's more illustrative to see this. Okay, for completion, just as the thermal conductivity versus temperature for the various geometries, but it's more illustrative to see the variation of the thermal conductivity compared to the membrane. So this is thermal conductivity of the phononic crystal compared to the membrane, which is 1 here. And here is the surface to volume ratio. And what you see is that depending on the surface to volume ratio, you have a variation of the thermal conductivity, which means that no matter how they are distributed, if you keep the surface to volume ratio, you can control the thermal, you can dial up a thermal conductivity. That's a message, right? And these are very low thermal conductivity. So this is a value of thermal conductivity at room temp of amorphous silicon. So you can get down to the level of amorphous silicon here. These measurements were confirmed by the group of Professor Nomura in Tokyo, where they had a similar arrangement, only here a stripe and a square pad, because they perform time differential thermal reflectivity, suspended structure, etc. And what is important is that they saw, like us, no major influence on the decay time, and more to confirm our data, no variation with respect to disorder at room temperature, both order and disorder. So at least the dependence of the thermal conductivity on positional disorder has been confirmed independently. This is very positive for us, and with a different technique, actually. Yes, that I don't know. This is a factor of 10 higher than what we have measured. I should have an intelligent answer like, but this is the cross the plane thermal. No, I don't know which one it is. I don't know. Actually, this this is a 10 micrometer bar. This is a much smaller sample than ours. Yeah. And so maybe there are effects already from the edges. Yeah. I know the paper has been out for review for 12 months now. It has come back, and I met Professor Nomura last month, and we talk about our perils of having our papers under review. Okay. And you can ask, well, this is all very well, but why don't you want to kill the thermal conductivity of silicon? Well, there are some good reasons for that. One has to do with the use of silicon in thermal insulating materials or thermal insulator interfaces. And the other one is the use in thermoelectricity. So there are many other patents dating back, but perhaps the most relevant for the kind of direct comparison to material and dimensions and thicknesses are these two patents. And I know that most of you work in theory, but the information in patents is extraordinary. The amount of details and considerations it really makes worth using patents as a primary source of information as well. So we were writing a proposal that went in 7th of April. And when I asked our technology transfer people, can you run a quick check on that? He said, bad news, Clivia. That's already been proposed. But of course, it's not the same idea. So we still have a chance to revive our proposal. So let me conclude. First of all, as stated before, the silicon membranes are a very good system to study not only confinement, but also mechanical and thermal properties, and decoupling in particular between optical and mechanical modes. We have explored order and the impact on thermal conductivity. We found that there is no impact of positional order in the thermal conductivity in the size regime where we have worked. We found that there is a way to tune the thermal conductivity in terms of the phononic parameters. Surface to volume ratio, this is incorrect. Surface to volume ratio has an impact, but depends on the geometry. And this basically means that one has to optimize the neck size and make it larger than the average phonon mean-free path. That's very important. So the neck size, because we still were not very clear exactly how the propagation happens, right? There is one picture that is using waves, as in photonic crystals. Other pictures using ray-type optics to show the motion of the phonons. We need to understand a little bit how the propagation actually takes place. But that is empirically, it's very important to have this neck, this amount of material left between holes, to be larger than the phonon, the thermal phonon mean-free path, the average. I think that's it, right? The perspectives. Well, I've already said them, I think. Yeah, not to worry. And as you see, we haven't even talked about fluctuations here, but it's too big, the samples, to talk about fluctuations. Maybe we have to make other type of disorder for that. Thank you very much for your attention. That's what I want to tell you.